In this problem, we're going to look at how the difference of direction up and down a river could affect the speed at which you're traveling. Now, this is because when you go upstream, you're going against the current, so you're having to paddle harder to keep moving, or really it's just slowing you down. But if you're going downstream, we say you're going with the flow. And so if you're paddling at the same rate, you're actually going faster because the current is working with you instead of against you. So in this particular case, we have a rower who's traveling both upstream and downstream along the same path. So we would say the same distance. So I'm just going to go ahead and call that distance D because I'm super exciting like that. And it takes him 45 minutes to go upstream, but only 30 minutes to go downstream. Now, it would be tempting to write 45 and 30 into these two positions. However, because our speed is going to be measured in miles per hour, we do need to convert them into hours. So 45 minutes out of 1 hour is the same thing as 45 over 60, which is 3/4, or if you prefer, a decimal, 0.75. So I'm going to go ahead and put it in as 0.75 hours, okay, because time is hours. And then downstreams is only 30 minutes. Well, 30 divided by 60 is the same thing as 1/2, which is the same thing as 0.5. So downstream only takes 0.5 hours. Now he is moving 2 miles per hour faster when he goes downstream. So then we could say that his upstream speed is R, would mean that his downstream speed, which is 2 miles per hour faster, is R plus 2. So we want to know how fast does he row in each direction? How fast is he moving in each direction, right? So what we're going to do here is we're going to remember that distance is equal to rate times time. Okay, distance equals rate times time. So my upstream equation is that distance is equal to R times 0.75. And my downstream equation is that distance equals R plus 2 times 0.5. I'm going to go ahead and put these in parentheses because I feel like that makes it easier to see where my decimals are. And so I'm not getting them mixed up with my time signs. Now, we need to figure out what R value makes both of these equations come out the same distance. Because again, you're going upstream and then you come downstream the same distance. So we're going to set the two distances equal to one another. Well, I'm going to go ahead and rearrange these just a little bit to make it easier to do that. So in my first equation, I can see that distance is really equal to 0.75 R. I'm just bringing that number in front of the R. In the second one, I need to distribute the 0.5, and I get 0.5 R plus 1. Now that I have these two ways to define distance, I can just set them equal to each other. 0.75 R is equal to 0.5 R plus 1. I want to solve for R, which is again the rate at which the rower is moving. And so we're going to subtract this 0.5 R over, which gives us 0.25 R is equal to 1. When you divide both sides by 0.25, you'll get that R is equal to 4. Now let's go back to the problem and see what does that really mean. Well, if R equals 4, that means that when he was paddling upstream, he was moving at 4 miles per hour. And if R is 4, then when he was going downstream and the current was working with him instead of against him, he was moving at 6 miles per hour. So how fast is he moving in each direction? 4 miles per hour upstream, 6 miles per hour downstream. Remember that as we continue through this topic, we're going to be getting into systems of equations more, and we're going to be moving out of the table format If you already know about those and you are comfortable with them, you are welcome to use those now instead of this. So you get to pick, but since most of y'all probably haven't done those yet, I wanted to make sure you saw the table strategy.